Hello, Honors Chem students. This is Mr. Keister here with you again today. This is the video for Tuesday, September 22nd, 2020, which is our scheduled 23rd, I believe. Yes, 23rd day of school for the fall semester. Always keep in mind, though, that the dates could change for a variety of reasons, but the lessons and the order that those lessons are presented will remain the same. Regardless of that. So let's look at today's schedule at our do now. So there wasn't anything to pick up today. From yesterday, you were to pick up discussion activity 2.1 part B and the 2.1B handout on the kinetic molecular theory. So your homework for today was to finish filling out the lab activity 2.1 part A assignment, including watching all 4 Eureka videos, 16, 17, 18, and 19 in Canvas. Hang on to that. I have the answers posted on the backboard. I did it this morning at 7, and also they are posted online on my answer keys page at that same time. Between the demos I showed you in class the other day, the videos that you were provided to you on Canvas, the online textbook reading, which was listed on the handout, and the 2.1A handout, you should have a pretty good grasp of the similarities and differences between solids, liquids, and gases, and the changes of state or phase changes between each. I'm going to go over that Part A handout a little bit today before we move on to Part B. You were to answer questions 1 and 2 only from discussion activity 2.1 Part B. Hang on to that. We're going to discuss that, and then I'll be finishing up with that today. So let's see. Today in class, I've already mentioned that. I am going to show you how to do pressure conversions today, which is on Part B, and do several examples on the front board here for that from questions 3 and 4, and the rest you will have as homework for tomorrow. So let's start off today by looking at the Part A handout, which kind of will help summarize where we are in regards to solids, liquids, and gases, and particle motion in the various states of matter. So as a quick review from last time, we looked at some demos regarding the gas and the liquid phases of matter. And remember, in the diffusion of gases demo, I sprayed some air freshener in the center of the lab area, and we saw that those air freshener particles spread out randomly. Obviously, they move because they spread out randomly throughout the room, I should say, in no particular order or no particular direction, but just do so randomly. In the next part, we looked at where I dropped food coloring into both cold and hot water, and we saw the difference in the speed of the particles liquid particles as they spread out randomly within the beakers, again based on the amount of energy they possessed. And then in the third one, we looked at thermal expansion of liquids by putting both alcohol, a test tube, kind of a rudimentary thermometer setup is what it was. One had alcohol in the test tube, the other had water. We placed them both in a hot water bath and saw how the liquid expanded, or the liquid particles spread out and went up the tube, just like a thermometer actually works. So we determined from that the liquid particles spread apart faster when the temperatures increased. We saw that also in the second part. We saw then that different types of liquid particles spread apart at different rates of speed because the alcohol particles moved up the tube or the thermometer much quicker than the water ones did. And we determined that was because of the stronger intermolecular attractive forces between the water particles as compared to the alcohol particles, which allowed the alcohol particles to move much quicker and more freely. So let's go on to the handout, which kind of summarizes the 3 states of matter. First of all, gas particles, of course, spread apart very fast. They have lots of empty space between them, and they're free to move about freely. The particles are arranged randomly. I would say actually very randomly. Okay, and the intermolecular forces or attractive forces between gas particles, there are none. This is which allows their freedom of motion. As a result of those no attractive forces, gases have both an indefinite volume and an indefinite shape. There's nothing holding them together, and so they take both the shape and the volume of their container. Since their particles can move about easily, gases are qualified as fluid. All right. Now, if I was going to draw a little more a precise drawing of a gas, of course, we've already drawn this before, where the particles are spread about freely, quick or quite wide apart. But one thing I would put on here, I'm going to put a couple of tails on them, like so, and those tails show that they are moving very fast, as we saw in the demo. Okay. Now we looked at liquids too. So liquid particles are much closer together than gases, but they still have some space between them so that they can move about and slide past one another. They are still arranged randomly. Still are. All right. Intermolecular forces. They do have them, but they're somewhat weak. All right. And we saw that they vary depending on the liquid. We saw that with alcohol versus water particles. Okay. As a result of weak attractive forces as compared to no attractive forces in gases, liquids do have a definite volume, but they still do not have a definite shape. So they have an indefinite shape. So they can hold their volume, but they still must take the shape of their container. And since their particles are still able to slide past one another, liquids also are fluids. So both liquids and gases are classified as fluids. Now, if I was going to draw a little more specific particle diagram of a liquid, again, we know that the particles are much closer together, okay, like so. I'll draw my little meniscus in here too, like that. And I'm going to give them one little tail or one little bar of speed to show that they still have the ability to move. All right, so I'm just going to give them one bar or one tail. Still can move freely, but not as fast, all right? Not as fast as gases. Because their motion is a little bit more restricted because the particles are a lot closer together, okay? Now let's talk about solids, all right? So particles of a solids are extremely close together. There's very little space between them, and they're not free to move about. Thus, their motion is restricted mainly to vibrating in place. Okay? Particles are arranged nearly always in an orderly fashion. Remember, when we talked about particle diagrams of solids earlier, most solids are crystalline in nature, meaning they have a definitive and orderly pattern to the arrangement of their particles. Very few of them are arranged randomly. Those are called amorphous solids. Glass is one example of an amorphous solid. They have very strong intermolecular forces, all right? Very strong, all right? As a result of strong attractive forces now between the particles, solids have both a definite volume and a definite shape. They can hold both their volume and their shape. So, solids are not fluid, all right? So liquids are fluid, they pour. Gases are fluid, obviously they can pour even though we can't see them. Solids though, no pouring there, all right? So solids are not fluid. Now, if I was going to draw a particle diagram of a solid, of course we've done this before, they're very close together. I'm not even going to put a little tail or bar on them because they don't have the ability to move anywhere. They just basically vibrate in place. So can't move freely. So I'm not even going to put a little tail on them because they can't move anywhere, okay? So anyway, a little more specific diagrams there for the three states of matter. And hopefully this little discussion here will help your understanding of both the similarities and the differences between liquids, gases, and solids. So I think that kind of takes care of part A of 2.1. Let's move on to part B. Okay, so I'm going to pull up here the part B handout, which are some key points of the kinetic molecular theory. We've kind of hit on these already, many of them actually. We just didn't say that they were part of the kinetic molecular theory, which states that the particles, which are atoms or molecules, depending on what type of substance it is, the particles of all three states of matter are in constant motion. The only difference between the three states of matter is the particle spacing and their ability to move freely, which is what we just said. So for gases, the kinetic molecular theory, or KMT, as we call it for short, is used to explain the many different properties of gases. Gases consist of large numbers of particles that have negligible volume in relation to the large amount of space between them. What that basically says is that the volume of the gas particles themselves is negligible. You can discount it as compared to the space between them. So the space between the particles is huge as compared to the volume of the particles themselves. There are no intermolecular forces of attraction or repulsion between particles. We've said that, they're too far apart. Gases have very low density, okay? Small mass, big volume of space between them means small density, okay? They're easily compressed. With a lot of space between them, you can push them together a lot easier, okay? Or expandable. Collisions between gas particles or with the walls of their container or with other objects within the container are elastic, meaning that no kinetic energy is lost by the particles during their collision, and thus their speed doesn't vary, all right? So when large objects collide like cars, of course, when cars like bump in the parking lot, they don't bounce back at the same speed they hit because some of the energy that they possessed before the collision is absorbed by the cars, and you see the cars' bodies crumple as a result of that. So some of that energy is absorbed by the cars, so they don't have as much energy to bounce back as they did when they first hit. That's not true of gas particles. They bounce off each other at the same speed they hit, so there's no energy lost there. We call those elastic collisions. Their energy, kinetic energy, depends on temperature. It's described by this equation, 1/2 times m times v squared, v being velocity. We'll get to that a little later on. By increasing the temperature then, heat energy is added to the particles, which increases their kinetic energy and thus their speed. Let me advance the paper here. The force of gas particle collisions with each other or with the walls of their container is what creates gas pressure, all right? Atmospheric pressure is just a little more specific term, speaking about air particles collisions with everything, all right? We call it air pressure or atmospheric pressure, same thing. But in general, the force of gas particle collisions with each other or with something else is what we call gas pressure. So gas particles move rapidly in constant straight line random motion and change directions only when they collide with something, either each other, other objects, or the walls of their container. We saw this in the demo in part A. The kinetic theory assumes that all gases are ideal gases, meaning all gases follow all the rules of the kinetic molecular theory at all conditions. But in reality, that's not true, because real gases deviate from kinetic molecular theory at extremely low temperatures or extremely high pressures. When you drop the temperature down enough, of course, the particles slow down. They end up getting closer together, and at some point, they get close enough to start having attractive forces between them, which is then going to cause them to convert to a liquid or undergo condensation. Same thing happens if you exert a high pressure on them. You push them closer together, they get attractive forces between them, they convert to a liquid. So real gases only deviate from ideal gas behavior at low enough temperatures or high enough pressures. But under normal lab or room conditions, gases are going to follow ideal gas behavior. Okay. Liquids. Let me move this up a little bit. We said the particles that make up liquids are also in constant motion, and they're still far enough apart so that they are free to slide past one another, although they are much closer together than gases, as we said. So liquids and gases are both classified as fluid. You mentioned that. They have the ability to flow and take the shape of their container. They both have the ability to diffuse or effuse. Okay, so diffusion we talked about, which is the spreading out of particles from one container into another. Effusion is where gas particles escape through small holes in their container, such as in a balloon. You know, no matter how well you tie off a balloon that you blow up, it's still going to deflate. You know, not because you're a lousy knot tire, but because there are tiny microscopic holes in the elastic that make up the balloon and that you can't see. And so as the particles are moving in there, they hit the holes and ultimately get out. So unlike gases, though, liquid particles are much closer together. Therefore, they have less freedom to move about. And they do have some weak intermolecular attractive forces between the particles. And a measure of how strong those attractive forces are in a liquid is called viscosity. All right, the resistance of a liquid to flow. The stronger the intermolecular forces between liquid particles, the more viscous the liquid and the slower it flows. Think about oil versus gasoline in regards to flow. Right? Oil doesn't flow nearly as freely as gasoline. Well, that's because the intermolecular forces in oil are stronger. Same goes with maple syrup versus water. Right? The stronger those forces are, the more resistant to flow it is, or the more highly viscous the liquid is. So liquids are much more dense than gases. The particles are a lot closer together. They're much less compressible or expandable than gases. You can compress or expand them somewhat, but not nearly to the degree you can gases. And liquids have these two special properties: surface tension, which is the force that pulls adjacent parts of a liquid surface together, decreasing surface area to the smallest possible size. You probably noticed this when you have a glass sitting on the tabletop and the glass sweats, the water vapor condenses on the outside of the glass and forms water droplets. They fall down to the base of the glass. You pick it up and you see water droplets all over there. But if you notice, those water droplets aren't little tiny droplets all over the place that they join together. That's because they have attractive forces between them. And so they form a much smaller surface area. That's called surface tension. Capillary action is the attraction of a liquid particle to a nearby solid particle. You see this in a straw or a tube where the water particles or whatever's in the straw are attracted to the solid particles of the straw itself. You ever notice if you put a straw in your drink, you don't even have to suck on the straw and the liquid will start going up the straw automatically? All right, well, and it's going up against the force of gravity, which is a pretty strong force. That's because of capillary action, the attractive forces between the liquid particles and the solid particles of the straw or tube. And then solids, a review of that. Unlike gases and liquids, the particles that make up solids are packed very closely together in fixed positions. Their motion, as explained by the kinetic molecular theory, is then therefore limited to mainly vibrating in a fixed position. As a result, solids are not fluid, so they have both a definite shape and volume. They have much stronger intermolecular attractive forces between them because they're so close together, and are, as a rule, somewhat more dense than liquids. Now, I mean, think about it. Most of the metals we looked at earlier in Unit 1, you know, their densities were anywhere from 2 or 3. Gold is 19, of course, but somewhere in there in the lower to mid single digits or lower double digits. Water, of course, is 1.00. So they're, as a rule, more dense than water, but not to a great degree. Gases, on the other hand, their densities, which are normally measured in grams per liter, if you measure them in grams per milliliter, they're like, 0.000 something grams per milliliter. So they're very, very small density. All right. So liquids and solids, comparatively speaking, are much closer together in density than either of those are to gases, which are far less dense. Okay. So as a rule, solids are more dense than liquids, but there are a few, for instance, cork, wood, or styrofoam. Those float in water. Those are solids. So why do you think that happens? Well, if you think about it, all of those things, cork, styrofoam, and wood, have spacing between their particles where air gets in there. And air, of course, is much less dense than either a liquid or a solid. And when you get air trapped in those things, their overall density then becomes less than the density of water or the liquid they're in, so they float. Okay, those are very unusual things. Most solids, of course, are also more dense than liquids. So I think that takes care of the handout. So let's now look at the actual part B. Okay. So you were to go ahead and fill this out based on the reading. All right. List the key points of the kinetic molecular theory. You don't have to go crazy there, but we just basically talked about all of them. So if you were asked to summarize that, how does the kinetic molecular theory explain gas pressure? We talked about that too. Remember, gas pressure is the force of the collisions of gas particles on themselves or other objects or the walls of the container. And it's the force of those gas particle collisions with each other or something else is what creates gas pressure. And then again, air pressure or atmospheric pressure are very analogous terms to gas pressure. They're only talking specifically though about the force of air particles colliding with each other or something else. All right, so now let's talk about how we convert pressure measurements from one system of units to another. We're going to talk about standard pressure, all right? Standard pressure. So I'm going to write this right here. So standard pressure is the average atmospheric pressure or air pressure at sea level, okay? At sea level. At 32 degrees Fahrenheit or 0 degrees Celsius, all right? Or 273 Kelvin. We'll talk about temperature conversions here soon, which is called standard temperature. So standard pressure is the average atmospheric pressure at sea level at standard temperature, all right? So all of these, 1 ATM or 1 atmosphere, 760 millimeters of mercury, 760 torr, 101.3 kPas, 14.7 psi or pounds per square inch. We use that in tire gauges. Or 29.92 inches of mercury. Those are all values of standard pressure in different units. So they're all equal to one another. So in making conversions between pressure units, what we do is use two values of standard pressure as a conversion factor, all right? As a conversion factor. So in other words, we're going to use dimensional analysis to convert between pressure units. Of course, you could use proportional reasoning too. So you could use two values of pressure to set up your proportion. So it could be done that way too. So let me show you how to do one of these. Let's do A. So we have 320 millimeters of mercury to atmospheres. All right, 320 millimeters of mercury to atmospheres. By the way, why is the measurement in millimeters of mercury? That's a length. Millimeters a measure of length. All right, let me show you that real quick. So here's a setup of a barometer. All right, so it's basically you have a glass tube here. It's got measurements on it, of course, and it's inserted into a reservoir of mercury, liquid mercury. We got mercury down here, okay, mercury particles all throughout here. Now, this is open on this end. So what happens here then is air particles, of course, are flying all around out here. All right, we got mercury particles in here. And they are, of course, flying into this tube. All right, so they're creating a pressure pushing down on this tube. Now, at sea level, at standard temperature, all right, this mercury, of course, is going to go up this tube. There's an opening down here. So these mercury particles are going to go up this tube, just like we saw with the alcohol thermometer and the water thermometer that we made in part 1 and part A. So they're going to go up this tube like so, but there's also a pressure being exerted by the air particles on the top, pushing down, right? So mercury's being lifted up from the bottom, but air particles are pushing down on it from the top. At sea level, standard temperature, the height of this mercury in this column is 760 millimeters. That's where the 760 millimeters of mercury measurement came from, okay? You'll also notice it says 760 torr. Well, the developer of the barometer, the mercury barometer, was an Italian by the name of Torricelli, Evangelista Torricelli, actually. And the unit torr was named in his honor of the invention of the barometer. So it's the same value, it's just a different name of unit. The atmosphere is the standard metric unit of pressure. We also use the kilopascal. The pascal is actually the SI unit SI standard unit of pressure. PSI is an English measurement that we use here in this country. 29.92 inches of mercury used to be used primarily by weather reporters to report, or meteorologists to report air pressure, especially during storms where it tends to get lower. Now we use millibars and a few other units as well, but these are all units of standard pressure. So anyway, to convert millimeters of mercury to atmosphere, so we take our 320 millimeters of mercury and we put it over 1, all right? And now we're going to use the value of standard pressure for millimeters of mercury in atmospheres as a conversion factor. Well, we want millimeters of mercury down here so that they cancel, and ATM's up top. The value for millimeters of mercury, as we just said, is 760. The value for atmospheres is 1. And so that's it. It's a simple dimensional analysis, one-step conversion. So 320 divided by 760. Our initial measurement is 2 sig figs. 320 is 2 sig figs. So again, with conversions, we round to the sig figs of the original measurement, and that comes out to be 0.42 ATMs. 2 sig figs there. Okay. So that's basically how you do it. So we start with the unit we have. We look at the unit we're trying to find, and we use those 2 units, values of standard pressure, as a conversion factor to get us from one to the other. From one to the other, I should say. So let's go to the back side. And this is a little different device, okay? Of course, here we drew a barometer, all right? which measures air pressure by, again, using a column of mercury. All right. This device here is called a manometer. All right. So this is a barometer. And this device over here is called a manometer. And it also measures pressure. All right. It measures gas pressure. All right. In a container by comparing it to air pressure or atmospheric pressure using a U-shaped tube. U-shaped tube. Of course, remember, a barometer uses a vertical, straight tube to measure air pressure using, again, a column of mercury. So you see here, this is a U-shaped tube. Now here's what I want you to understand how this thing works. So the gas is in this container here, and it's connected by an opening to this U-shaped tube. And then the other end of the tube is open to the air. It's open to the air. And then again, we have mercury in this tube. All right, we have mercury in this tube. So here it's showing the air pressure is 730 millimeters of mercury. All right. So let's look here at these three. Okay, now I want you to notice something here. So this is 4A. In 4A, I want you to look here. The mercury is pushed down on the one side by the gas in here. It's pushed down on the other side by the air particles. So here the gas particles are pushing down, and here to the outside, the air particles are pushing down. Are they pushing down with an equal force? Well, the answer to that is no. If they were, that would be straight across on both, be the same height on both sides. But look here, it's being pushed harder on the gas side than it is on the air side. It's down farther here and up higher there. So what that's saying here in part A is that the pressure of the gas is greater than the pressure of the air. Greater than. So now how do we figure out what it is? Well, we know what the air pressure is. It's 730 millimeters of mercury. The difference between these levels here is going to tell us how much greater it is. So the pressure of the gas is equal to the pressure of the air, 730, plus, it's greater, right? Plus the difference between these two readings. 127 minus 84. All right. Just take the larger one minus the smaller. And so let's see, that's 43. So that would then say the pressure of our gas is 773 millimeters of mercury. So again, I want to make sure you understand why this is so. So the pressure in here is 773. The pressure from the air on the other end is 730. Since the pressure in the gas chamber here is larger, it pushes down on the mercury with a greater force than the air does up here, and thus the level is lower here than it is on the other side. Now look in letter B here. Just the opposite is true, all right? So here the air, again, is up here, and the gas pushes from this side. Look here now. The level of the mercury is much lower on the air side than it is on the gas side because the air particles are pushing harder from the air than they are from the gas. So in this one, the pressure of the gas is less than the pressure of the air. So the pressure of the gas then is going to be 730, which is the air pressure. Now it's going to be minus the difference between the two because it's less. And the difference here is 130 minus 26, I think, if I can read that correctly. Yeah. So the difference there is 104. So 730 minus 104 is 626 millimeters of mercury. And again, that makes sense because the pressure of the air is much larger than the pressure of the gas, as evidenced by the mercury column levels here, and that bears that out here. Now, in this last one here, I want you to look. So again, here's the air pressure pushing from this side, the gas pressure pushing from this side, and look at the levels of mercury in the U-shaped tube now. They're exactly the same on both sides. What does that tell you? Well, it tells you that the pressure of the gas is equal to the pressure of the air from the outside. And so the pressure of the gas now is the same as the air pressure, which is 730 millimeters of mercury. Okay? The difference, 95 minus 95, is 0. All right? And so 730 plus 0, or minus 0, is 730. Okay? Okay, so for your homework tomorrow, I want you to finish the conversions on the front side of this paper, and then also do number 5 here with the manometer like we did here, and then number 4. So I think that takes care of today. So until next time, this is Mr. Keister signing off. Keep working hard, everyone. Stay safe, and I'll catch you next time. See ya.